So, in your class at Augustana, you're encountering some more complicated nomenclature than what we talked about here at St. Ed's. So I want to take a moment and kind of go through how this older system worked. All right. So the first one is the ic and the us endings. This came about because a lot of the discoveries in chemistry were made by people that were classically educated in Latin and Greek. So they named these chemical compounds using these Latin and Greek terms. Unfortunately, I personally think it's out of date, but allegedly they're teaching it at your college, so let's go through it. So the ic and the us are suffixes that indicate which oxidation state or which charge a certain ion will have. Okay, so let's consider this example. You can have cupric oxide, or you could have cuprous oxide. And so the question then becomes, what is what? And so what you have to remember when you're looking at this is that when there are two oxidation states, the ic is the higher oxidation state, and the us is the lower oxidation state. I'm not sure if your teacher wants you to memorize all the oxidation states for all the transition metals. And by the way, when I say oxidation state, I'm referring to charge. I'm not sure if you need to memorize all the charges for the metals, but that's where this comes from. So copper will form a +2 most commonly, or a +1. All right, so cupric is the higher one, so cupric is the 2+, and cuprous would be +1. So now to write the chemical formula, so I'm almost certain that he's giving you a name like this and having you write a chemical formula and not do vice versa. Cupric oxide, copper is 2+, and oxygen is 2-. We know that they are simply going to cancel each other out because they're equal and opposite, so our chemical formula would be CuO. When you're faced with cuprous oxide, so copper is +1, oxygen is 2-, you are going to need two of the +1 copper ions to equal the oxygen -2. Or another way to think about it is to crisscross, like we did it here at St. Ed's. So the 2 over here is going to come down to the bottom of the Cu. The 1 is going to go over to the oxygen. You need 2 copper ions to counter the oxygen, so the chemical formula for this example would be Cu2O. So that covers the ic and the us endings. So the other thing you talked about in your email was how to deal with transition metals. All right, how do the Roman numerals relate to transition metals? So let's go in both directions. So let's say I give you a compound, all right, copper 2 sulfate. What's the formula for a copper 2 sulfate? All right, so copper is 2+. I know that because it tells me, all right, it's very straightforward. That's why this system is really much better than the old-fashioned ic and us system, because this system is called IUPAC. Tells you exactly what the charges are. So copper is 2+, sulfate is SO4 2-. If you haven't already, I know I really didn't push this here at St. Ed's, but I would memorize the polyatomic ions. Know the symbols, know the charges. It will save you a lot of grief. Copper is 2+, sulfate is 2-, so my chemical formula will be copper or CuSO4. Let's do another one. Copper 2 sulfide, something different. Chloride. Copper is 2+, chloride is -1. How do you get the -1? Well, you look at the periodic table, and chlorine is in group 7. It has 7 valence electrons, so it's going to take on 1 additional electron in an ionic system in order to have a full octet, in order to have 8 outer electrons. So copper forms +2, chlorine forms -1, so my chemical formula is CuCl2. All right, now let's consider a different example. So let's now erase this, and let's go in the opposite direction. Let's say I give you the formula, and you need to figure out the name. So let's look at Fe2O3. All right, so I'm given this, it's some kind of iron oxide, but if I just say iron oxide, that's very imprecise. All right, so I have oxygen. I know oxygen has a 2- charge, and I have 3 oxygen atoms. So because I have 3 oxygen atoms, oxygen can be said to contribute -6 to this molecule, all right, a total charge of -6. If oxygen is -6, then the iron must have a +6 charge for them to be equal and opposite, because they have to be equal and opposite in order to exist. So oxygen or iron is +6, and because I have 2 iron atoms, the charge must be equally distributed among both iron atoms. So, that's going to make this a +3. So my chemical name would be iron 3 oxide. Another thing, the "ide" ending is a pure element. All right, so whenever you see "ide", think pure element, with the exception of hydroxide. That's the only one exception. All right, ate, ite, or anything else you might think of, those are all polyatomic ions. So you have to remember that ate and ite are suffixes for polyatomic ions. Sulfate, sulfite, nitrate, nitrite. All right, so whenever you see any of those, you must remember that you're dealing with polyatomic ions. All right, but let's erase this for a moment and let's do one more example. So looking at my periodic table, trying to keep it fresh, let's do CrO4. All right, so we have chromium, we don't know the charge. Oxygen, there are 4 oxygen atoms. Oxygen has a -2 charge, so if I have 4 oxygens at a -2 charge, oxygen must have a -8 component of the molecule. It must receive 8 electrons, essentially. Because oxygen is -8, chromium must be +8. So the name of this compound would be chromium 8 oxide. But actually this compound doesn't exist because I should have looked at notes before doing this. So let's actually look at something that does exist. All right, oxygen has a -2 charge. There are 2 of them, so oxygen contributes -4. Titanium must be +4, so this is titanium 4 oxide. All right, and then lastly, your email mentioned the chlorate, chlorite, etc. So this is what you kind of have to do. You have to memorize the system. All right, so let's think of an example. These are oftentimes acids, or they are polyatomic ions involving oxygen. And so the one with the most oxygens will have a per-8 ending. The next one is 8, the one after that is ite, and the one finally is hypoite. Okay? As an example, HClO4. This is going to be called let's go back. NaClO4. All right? Sodium perchlorate. If I take away an oxygen, it would be NaClO3. That's sodium chlorate. I take away another oxygen, that's NaClO2. That's sodium chlorite. I take away another oxygen, NaClO, or NaOCl, they're interchangeable, would be sodium hypochlorite. So that's how the system works. The most oxygens is perchlorate, then comes chlorate, then chlorite, than hypochlorite. Now, when you consider acids and bases, how you name those, well, the bases are going to be named either sodium hydroxide, or potassium hydroxide, or you're going to have some bases that are going to have their own particular names. All right, and I don't think you're going to go into that kind of detail with your class, understanding that amines, for example, act as bases. In terms of acids, they are named in a particular way. So HCl, hydrochloric acid, HF, hydrofluoric acid. If you ever wonder how to spell fluorine, don't spell flour. It's the opposite of flour. H2SO4, sulfuric acid. Remember those rules about the ick and the us? So with the acids, if I take away one of the oxygens, the ick becomes an us. So H2SO3 is sulfurous acid. H3PO4 is phosphoric acid. And then H3PO3 would be phosphorus acid. So just remember that the ick and the us, when it corresponds to, you can't see that so far down. When the ick and the us, when we're talking about an acid, the ick has the most amount of can't talk anymore. The ick has the most amount of oxygens, and the us has one less oxygen.